Section 29.4, the momentum of a photon and the Compton effect. So we're going to imagine an experiment where we have an electron that's at rest and we send in an X-ray photon, which is just X-ray, electromagnetic radiation. We're sending light in, happens to be in the X-ray range in terms of frequency and energy. But we know that light can behave as a particle. And here's some evidence of how it can behave like a particle, like a photon, in that when the X-ray strikes the electron and causes the electron to recoil, to bounce off in some other direction, the X-ray photon is then scattered in a different direction, right? It bounces off of the electron and they split. Due to the conservation of energy, the fact that the electron is now moving, it gained energy. That energy had to come from somewhere, and it actually came from the light itself. So the scattered photon has a smaller frequency or a larger wavelength because it has given some of its energy to the electron. So this is known as the Compton effect. We're going to take a closer look here. So the momentum of a photon we can calculate with h, Planck's constant, divided by the wavelength of the light of whatever interest it is, right? But momentum and energy are both conserved in this collision. It's an elastic collision, which means we can look at the initial momentum of the incident photon, and that will have to be equal to the final momentum of the scattered X-ray photon as well as of the electron. Similarly, the energy needs to be conserved. So if we have some energy of the incident, then that's going to have to be equal to the energy of the scattered, which we're going to note with a apostrophe or a prime symbol to note that that's the scattered one. Just write scat, and then plus the energy that the electron has, which the energy the electron has, we can just write as kinetic energy. Cool. And we know that the energy of the photons we can calculate going back to our energy of light equations, right? Which, if we want to work in terms of wavelength, we could calculate it with h times c divided by wavelength. Or in other words, for the scattered one, it would be h times c because the speed of the photon is constant. That's not changing. But what does change is the wavelength or the frequency it's at. So that would become lambda prime plus the kinetic energy of the electron. 1/2 the mass of the electron, 9.11 times 10 to the negative 31, times the speed of the electron squared. So there's one relationship. And you could combine this along with the conservation of momentum to show the following equation on the bottom, that the wavelength changes, lambda prime of the scattered photon, is bigger than the initial wavelength by this quantity on the right. Planck's constant divided by the mass of the electron divided by the speed of light times the quantity of 1 minus cosine of theta, where theta gives you the angle of the scattered X-ray photon. It can be as small as 0 if it just keeps going in a straight line, or as large as 180 if the incident X-ray photon bounces off and goes the opposite direction. So with this in mind, let's take a look at a conceptual example. So solar sails and the propulsion of spaceships. One propulsion method that's currently being studied for interstellar travel, you can look it up on the internet, solar sails, it's a thing, uses a large sail. The intent is that the sunlight striking the sail creates a force that pushes the ship away from the sun, much as the wind would propel a sailboat. To get the greatest possible force, should the surface facing the sun be A, shiny like a mirror, B, black, or C, either shiny or black, since the same force will be created for either surface. So I want you to go ahead and think about this, come up with an answer that you feel comfortable with and an explanation. It can be totally wrong, but you should have something. So please go ahead and hit pause now so you can do that. All right, I'm gonna trust you hit pause. So let's take a look at these different responses. If it's shiny, then the sunlight is going to reflect off of the sail. If it's black, then the sunlight will be totally absorbed into the black surface. So we have to figure out which one is better, or if there is any difference in propelling the sail forward. To think about this, there's a useful analogy that our book looks at way back in the momentum chapters with linear momentum, where it compares raindrops striking the top of a car versus hailstones striking the top of a car. Because raindrops fall and just splatter, so they get absorbed by the top of the car, much like the black surface. Hailstones bounce off of the top of the car, much like the shiny like a mirror would cause the photons to bounce off of the sail. So which has more effect? Well, if you think of hailstones versus raindrops, I know that my car is in much more danger from hail striking it than from raindrops striking it. Why is that though? Well, for it to go down and then change direction is a much larger change in momentum. So that's imparting much more momentum forward or down, depending on how you look at it, for it to totally bounce off of it and send it the other way. Versus if something just absorbs it, it still is going to transfer all of its momentum, but it won't be twice as big. So what we see here is that to get the maximum amount of force, we want to make it shiny like a mirror. And then the photons will bounce off of the mirror, and as they're bouncing back the way they came, that will send the solar sail forward even more so. So there we have the momentum of a photon and the Compton effect.